This podcast is about half-life and how to do half-life calculations, and then a few of the uses of nuclear chemistry. So what half-life is the time that it takes for half of a mass of something that's radioactive to decay. So for half of the amount to be gone, that is one half-life. So here's just a picture with the half-life of what starts out as uranium-238, which is radioactive, and then as it decays through alpha and beta and beta and alpha and alpha and alpha radiation, it goes down, it keeps decaying until it gets to lead-206. And then it's stable, and then it stops. So this shows the graph of the decay of carbon-14, which has a half-life of 5,730 years. So what happens is, if you were to start out with 100 grams of carbon-14, after 5,730 years, you would have 50 grams left. You'd have half of the original sample. And then if you waited around another 5,000 years, or 11,460 altogether, you'd have 25 grams left of your original sample. And then after another 5,000 years, 17,000 altogether, you'd have 12.5 grams, and then it would keep going and going and going. Every 5,000 years, it would be cut in half. In theory, would you ever have zero left? And in theory, you would not, because it would just get smaller and smaller and smaller. As a practical thing, when it got too small to measure, then you couldn't measure it anymore, but there would still be some atoms left. Carbon-14 dating is when you you measure the amount of C14 that is left in something that was living, and everything that's living has a certain amount of carbon-14 in it when it is born. Trees and plants and animals, and when they become fossilized and they're old, you can figure out how old they are by how much carbon-14 is left. So here we're going to do some half-life calculations and problems. And the best way to do them is really just by hand. And what I want you to do here is go through and try to solve them. And if you get stuck, then look at the key or ask your teacher. And try not to check the key until you've already tried them. So just a quick note, what we've done here is, what I do is for every half-life, I do one arrow. So starting with 15 grams, 30 years is a half-life, so I label it with an arrow, cut it in half to 7.5, a second half-life, 3.75, a third half-life, and that gives me the final amount. And that's how I solve these problems, is I label each half-life with an arrow to show that it's another half-life and it's going to get cut in half. So again, finish the rest of the problems, try them on your own, and use a calculator if you need to, and then play the video and check your work. So after you do these problems, then go back and do the homework that you have to do in Moodle. So what are the effects of nuclear radiation? There's lots of negative effects. It can be used for good and bad, but overall, the electromagnetic spectrum, radiation consists of energy, and at a higher frequency, it will have a higher energy. So if we look at the electromagnetic spectrum, we saw this way back when we looked at light and electrons, but the very, very highest energy waves are gamma rays, which is the highest energy gamma radiation. So all the way at the end of the electromagnetic spectrum. How is it measured? It's measured using something called a Geiger counter, and that's how we can measure how much radiation there is, either natural or unnatural. Effects that radiation has on humans, there's lots of effects, but overall they all come down to they damage cells. They damage skin cells and growth cells. That's why people who are on radiation for cancer, the radiation kills the cancer cells, but it also kills like hair cells and things like that. So it definitely damages cells. Iodine can be used to absorb radiation in case of accidental exposure. So people who live near nuclear power plants actually have to have iodine on hand in case there was ever an accident. They would take iodine, and the idea is that the iodine would absorb the radiation more than their bodies. So nuclear weapons, there's two basic types of nuclear weapons, and those are fission and fusion. And fission is where two nuclei combine, and that's what you have in an atomic bomb or the uranium bomb. And then fusion is where nuclei split, and when they split, they also generate energy, and that's the type of reaction that was in the hydrogen bomb. And how do they work? These are very simplified, but this is the radioactive material, and they have a primary detonator which goes off, and it starts a chain reaction in the radioactive material. The energy goes in, and then that reaction causes a chain reaction which, goes crazy. Nuclear power plants involve a nuclear reactor over here, and it does, notice that it is lead lined to keep it safe. And what it does is generate lots and lots of energy, which generates steam, and then the steam powers a turbine, and then the turbine actually generates electricity. And those big cooling towers that we see that look really, like white smoke is coming out of them, those are just to cool down the steam back into water so that it gets recycled.